Okay. Okay, so let me start this session by introducing myself. I am Moina Ghoshal. I am a PhD student at Indian Institute of Science Education and Research, Kolkata, and I have been assigned as the TA for this course, which is entitled as Fundamentals of Spectroscopy, which was instructed by Professor Sayan Bakshi and Professor Anirban Hajra. And this is assignment related questions regarding week number 7, where I am going to discuss some questions which will be helpful for you to solve your assignment questions. And then you will learn something. If you have followed these lectures, the lectures throughout up to now, then you will be able to follow me what I am going to say. And then maybe you will learn something that you don't know up to now. So there will this is an interaction session, and hence I request you to please ask me questions if you have any problem. Okay. So starting, I am just recapping the last week assignment, what I have discussed. So this is all about the last week assignment, what I have discussed. Okay, so our discussion started with normal spectroscopy. What is spectroscopy? Why it is necessary for spectroscopy is necessary. Spectroscopy is nothing but light matter interaction. And then from that, line with broadening, different kinds of broadening, homogeneous, inhomogeneous broadening, that things were discussed. Then electromagnetic spectrum. In electromagnetic spectrum, which part is responsible for what kind of spectroscopy, that was also discussed. And then one by one, every spectroscopic techniques we were going to discuss. So we have discussed already this rotational spectroscopy. We have discussed already vibrational spectroscopy, and in the last live session, I have also discussed about rotational vibrational spectroscopy, which is also known as row vibrational spectroscopy. So in the last class, I have discussed about this row vibrational spectroscopy. This happens that it is seen that we have read this rotational and vibrational spectroscopy separately, but it is seen that in every vibrational level there is some rotational levels associated with it. So whenever you are just discussing about some vibrational transition, always there is some rotational transition is associated with it. And this was proved using the spectra of CO in CCl4. And there was an appearance of rotational levels in the spectrum. Then from that, dissociation energy was calculated, and then the appearance of vibrational levels along with rotational levels in the potential energy diagram, that was discussed, that in every potential, in every vibrational level, there is some rotational levels associated with it. And all the calculations regarding this was done considering V equals to 0 state is the ground state, and V equals to 1 state is the excited state. That means your vibrational levels is fixed, and then all the values of this J value, like rotational quantum numbers, they were varied. Okay, and then it was the turn for Born-Oppenheimer approximation. They have treated this this rotational and vibrational levels separately. That means whenever there is some rotational motion and vibrational motion, they are happening together, then you can separately treat this rotational and vibrational energy. Then it was discussed that other than this fundamental transition, there could be two types of band. One is P branch transition, another is R branch transition. These two corresponds to the selection rule. P branch transition corresponds to selection rule delta J equals to -1, and this R branch corresponds to transition of delta J equals to -1. And hence, for this selection rules also derived that for P branch transition, delta J should be equals to -1, and for R branch transition, this delta J must be equals to +1. Then classical description of simple harmonic oscillator was given. That in a normal case or in a classical case, what is a simple harmonic oscillator? That means the restraining force is proportional to the force applied. Okay, so if from that point of view, it was shown that the total energy of a system is constant. That is, if you add kinetic energy, if you add potential energy, and it was also there was a problem regarding that, which showed that yes, the total energy of the system is independent of any kind of this x, k, or omega t, etc. It is completely constant. Then from this classical description, there was it was a shift to this quantum mechanical description of harmonic oscillator. Okay, and there the discussion was on wave function and energy calculation. What should be the wave functions for each energy levels? What should be the energy of this level? That was also calculated. Next, the calculation of energy difference between two states, it was also calculated. Earlier, when Professor Sandbakshi has discussed about that, he has discussed in non taking the energy uh, of these rotational or vibrational levels, and then from that he has shown that this would be the energy difference. It was shown to be H omega, H cross omega or H nu. Suppose I am writing H cross omega. But now here in Professor Anirban Hajra has shown that using this ladder up and ladder down operator, you can easily convert a level or a particular wave function to its higher analog or its lower analog using ladder up and down operator respectively. Okay, so here there you have seen that whenever a ground state operator is operated by some ladder operator, it will be also become the eigenfunction of this Hamiltonian. And from there, you have seen that this the energy difference will be increased by h nu, h cross omega. So by that way, using this ladder up operator, we have calculated the energy difference between two successive levels. Then we have found that the wave function of the other energy levels of the with respect to the ground state. What I have told now, that with the help of this ground state wave function, we can calculate the wave function corresponding to other excited states. Using this ladder up operator or ladder down operator, you can get the energy levels which are below this excited state. Or we taking this excited state energy level, you using this ladder down operator, you can get energy of the lowest levels. Also, in the final lecture, there was a discussion on this total kinetic energy in terms of two coordinates. One is center of mass, which was represented as capital X, and relative mass, which was represented as small x. In the total kinetic energy, suppose there is a diatomic molecule. For these two masses are there, two positions are there. I can convert these two positions into a center of mass motion and a relative motion. And we have showed that the total kinetic energy of the system, you can write it in terms of kinetic energy corresponding to center of mass and kinetic energy corresponding to the relative mass. Now, the derivation was done on the selection rule for vibrational transition in terms of transition moment integral. Whenever you go for spectroscopy, if you are going to calculate or if you are going to derive any kind of selection rule, or that what should be the selection rule, then you must need this transition moment integral to be non-zero. Otherwise, transition will not be feasible. So, transition moment integral is defined as psi star. If psi f is my final state, psi star mu psi I, where I is the initial state. This need to be non-zero. Under this condition, only the transition will be allowed. Okay. So this, so the condition that will fulfill this condition, that is psi f star mu psi I is not equals to 0, that will be the selection rule. Okay. So this was all about the previous week's assignment. Was I have discussed about the last week about this rotational vibrational spectroscopy. So now I'm moving to this week's content. So one by one I'm going. So in lecture 32, Sayan Bakshi has taught this, and after that, what I have discussed. Yeah. So what I have discussed in the last discussion, that how these P branch R branch lines are coming, but then there was a shift to origin of this vibrational transition or vibrational spectroscopy. So our discussion on this rotational vibrational spectroscopy was stopped there. Okay. So we are now resuming this discussion, that in the P branch it was shown normal in this and okay. So it was shown that in P branch or R branch, whatever it is, the difference between two successive levels will be equal, and that will be equals to 2p. But it was shown that in the real spectrum, it seems that these P branch lines are coming closer to each other, whereas P branch lines are getting far away from each other, but R branch lines comes closer to each other. So, and for this, the two concepts were discovered. That is the concept of anharmonicity, that is the harmonic oscillator concept is not there, and second and foremost condition is dependence of B on vibrational quantum numbers. If you remember in the previous discussion when we have discussed that total energy was discussed to be the B value of V equals to 0 level was considered is equals to B. B value was considered to be equals to B of equals to 1 level. Okay. So it was also discussed. It was discussed that you in the for both the cases we have taken the same B value, but this is not true because there was a dependence of B on this vibrational quantum number. How? Because B is depends upon in this equation of B. You can see there was a dependence on moment of inertia. Now this moment of inertia will also depend on bond length mu r square. You know this is B proportional to 1 by I. And I is equals to mu r square. So I will depend upon this R. Okay, so bond length. So if you are going to higher vibrational level, your bond length will change. So how can we expect that your B will not change? Your B will must be changed. B must be changed. Okay. So finally, there was new expressions for corresponding to B and depend upon V. It was defined as B into B minus E minus alpha into V plus half. So, for one thing you can clearly see here that as if considering this B is constant, which is the hypothetical rotational constant that the molecule has at the bottom of the potential energy well. Okay. If this is constant, then if you are increasing V, what will happen? Your BV will decrease. That means your B value will get decreased if you are increasing the vibrational quantum numbers. Okay. And then there was a derivation of this energy of this pre-branch line. It was given by, I'm writing it over here, that is nu bar p. Just one thing, and this another nu bar p for p branch. I am writing it. I have the expression with me. Nu bar e minus 2 nu bar e I minus j double prime into B0. B0 corresponds to the B value of the zero level. Okay. B1 minus J double prime into B0 minus B1. Okay. So it is the expression for P branch. Okay. So you can see here that whenever B is equals to, suppose the initial condition what we have thought about in the previous discussion, that the two B values are equal in the vibrational levels. Please understand it clearly that you have initially guessed that your two B values, that is B value for the rotational levels which are present in the ground vibrational level, the B value is equal to this B value of the rotational levels which is present in the excited vibrational level. The B values are not equal. B value will depend upon V. Okay. So it will depend upon V, that is vibrational quantum numbers. So in previous case, you have just neglected this term because if B0 is equals to B1, this term will get cancelled. Now you can see that P bar will get decreased as you increase this J prime. So the lines will come much closer to each other in the P branch. Sorry. So if you get put this B, sorry, I made a mistake. So if you put this equal, not equal sign, you can see that this term is, what will be this term? This B0 minus B1, I have said that B0 greater than B1. Always if you increase V, your B will decrease. So this term is always positive. So the energy difference, suppose it is here, equal difference, but difference is getting decreased. That is, your one line is coming here, another is coming far apart, another is coming another far apart, because the difference is increased. Okay. So if you do the same thing for the R branch, you can see that for R branch, these lines are getting closer to each other. Okay, and remember that this J prime is the initial quantum number of the ground state vibrational levels rotational quantum number. Okay, the rotational number corresponds to vibrational level in the ground state. Now there was a calculation of B0 and B1. How this was calculated? This was calculated using the proper lines in the P and R branch. It was shown that suppose something is in pre-branch happening from J is equals to 1 to J equals to 0 level. The same thing on R branch will happen from J equals to 1 to J equals to 2 level to satisfy this condition of delta J. So you can see that the two ground states will be equal, but the excited states are different. So if excited states are different, you know how to calculate the difference between these two B lines. What I'm saying that suppose you have the same J level. This is ground level. Ignore my drawing. Just understand the concept. So this is my ground J level. I'm changing the color. Yeah. Yeah. So suppose these are my energy levels. Okay. Corresponds to, I'm just like drawing a short ordered drawing. V equals to 0. These are my energy levels corresponding to V equals to 1. Okay. So a transition from this is suppose J is equals to 1, J is equals to 0, J is equals to 2. Similarly here, this is J is equals to 0, J is equals to 1, J is equals to 2. So a transition from here to here corresponds to P branch. Same transition here to up level, this is R branch. So if you know these two frequencies, you can easily calculate this much difference, and you know what should be the difference between these two rotational levels in terms of B. So you will be able to calculate B1. Okay. Similarly, if you have taken these two lines which have the final excited state same, that is the same final excited state but originating from different ground vibrational rotational level. From there, you can calculate V0, that is the rotational constant for the ground. And then there was a discussion that there should be something which corresponds to delta J is equals to 0. That was named as Q branch. Okay. So in the next lecture, there was a discussion on vibrational modes in polyatomic molecule. There was a discussion on normal modes of vibration. Other than translation and rotation, the vibrations that a molecule exhibit, this is the normal modes of vibration, and it depends upon the atomicity of the molecule and what should be the shape. Okay, for a molecule of n atomic number, that means n atoms are there in the molecule. If there is the case, so there should be 3n number of degrees of freedom. Okay, suppose molecule 1d1 atom, I can move it from x, y, z in the 3 directions. So if I have n atoms, this is a normal math. So if I have n atoms, I can move it to 3n directions. Okay, so 3n number of degrees of freedom are possible. From this, for linear molecules, you can see 3 translational motions will be there and only 2 rotational motions will be there because they are linear molecules, they are inclined to the plane. But for nonlinear molecule, there should be 3 different rotational will be there. So now remaining number of modes will be due to normal modes of vibration. So for linear molecule, this normal modes of vibration is 3n minus 5, but for non-linear molecule, this total vibration is 3n minus 6. Okay, and then there was a discussion on IS spectra of water that showed 3 bands there. Okay, so if you put for water, n is 3. So 3 into 3, there will be 9, and you know if water is a non-linear molecule, so 3 into 3, 9. So minus 6 will be 3. So 3 non-linear, 3 modes will be there. But in carbon dioxide, if you calculate which is a linear molecule, also triatomic. So if you put, it will go in this category. So 3 into 3, 9 minus 5, this will be 4. But you can see only 2 bands are there. There was a discussion that the 2 bending moments of carbon dioxide is equal. Okay, that means they will give the same position peak. And then using harmonic oscillator approximation, energy corresponding to a normal mode is defined. That is defined in this formula. That is nu bar corresponds to a normal mode Vi. It can defined as Vi plus degeneracy of this ith level divided by 2 into nu I bar. Okay, and from that, if you put this Vi is equals to 0, you can calculate this total energy or total 0 point energy of all modes. Okay, so to calculate the 0 point energy of all modes, it was calculated to be, this will depend upon nu bar is equals to half nu bar 1 plus 2 by 2, I'm writing in form of degeneracy, 2 by 2 nu 2 bar plus 1 by 2 nu 3 bar. Okay. So this was the calculated 0 point energy for water molecule. Okay. So then the next lecture, there was a discussion on symmetry elements of a molecule in the light of group theory. So you don't have some that much idea about group theory, but for now you just understand some operations you have learned in the inorganic chemistry. Cn sigma e. What is Cn? Cn is the n-fold rotation axis. Suppose if for n, if you rotate it by 360 by n, it will give you the identical conformation. So this is the Cn axis. Sigma means if it is a plane that will bisect an atom or bisect something, and the two sides of this plane will be identical. And it is the identity of every molecule will have this one, this E identity element. Okay. And then there was a concept of discussion on the concept of point group and character table. Yeah. So there was a discussion on point groups and character table. It was shown for water molecule that water molecule belongs to C2B point group, and the character label is shown. And also, AB symmetry designation with respect to C2 for water molecule is shown. That if operating something on water molecule with respect to C2, if this is giving the symmetry configuration, then it will be called A. If it is giving asymmetric configuration, then it will be B. Okay. And this AB naming was given in terms of C2. Okay. Then the designation of the symmetry of water vibrational modes from character table that was also discussed. Then symmetry of the wave function of any vibrational level, that was also shown, that what should be the symmetry of this wave function at any vibrational level, and upon this symmetry you can calculate this transition intensity. What should be? I'm writing again this equation for transition moment integral. So psi f star mu psi I d tau. Okay. So if psi f and psi I, if these two have the same symmetry, and then mu should have some symmetry, that means this total multiplication will give you a1 symmetry, that is totally symmetric configuration. Okay. So for a totally symmetric configuration, the transition intensity will be maximum. So for a successful transition, your psi f and psi I will follow some symmetry, which will be multiplied with mu to give this AI. And then under that condition, this transition will be much more facile. So this was a discussion on this small discussion from this group theory. And for water molecule, how should be the symmetry, dependence of the symmetry on this transition intensity, etc. Now, in the lecture 35, there was a discussion on the selection rule of rotational vibrational spectroscopy in terms of another symmetry to two modes, which is parallel mode and another is perpendicular mode. Okay. So this was named due to the direction of this transition dipole moment with respect to C2 or with respect to your principal axis of symmetry. If this is aligned parallel, then you can know this is parallel mode. And if it is the other side of this if you will form a perpendicular shape, so this will be perpendicular mode. Okay, and it was shown that what is PR band profile and what is PQ band profile. The selection rules was also discussed for parallel modes. That is, for parallel mode, the vibrational selection rule for both these remains the same, but for perpendicular, another addition was in the rotational selection rule, that is delta G is equals to 0. That was not included in the parallel one. Okay, so delta G equals to 0, you have seen this corresponds to this Q band. That's why it was also discussed that this Q band will be there. You will only see Q band if there is perpendicular mode of vibration. And it was seen that for bending modes, it was seen that this angular momentum that was that contributes to the angular momentum that contributes earlier to the rotational levels, it now contributes to the vibrational level due to bending. For that, delta J is equals to 0 becomes allowed, and you can see this rotational transition due to Q branch. Okay. Next, there was a discussion on skeletal vibration and group vibration. So what is skeletal vibration? Skeletal vibration defines if you have understand this concept, that is what is bending vibration, what is stretching vibration. So if they are coupled to each other, that means if this is some vibration that is a product of coupling of so many vibrations, and whereas group vibration is completely different. Group vibration is, this vibration is independent of the vibration of this other molecules or other part of the group. Okay, so it depends upon. So this generally occurs in the higher frequency range of 700 to 14,000 centimeter inverse. Writing it again. The skeletal vibration occurs at nearly equals to 700 to 14,000 centimeter inverse. And group vibration generally, that depends in the group that is present. This generally happens from what I say 15,000 to almost 4,000, 5,000 or so on. Okay, I'm just writing 4,000. That doesn't mean above 4,000 it is not possible. Okay, so and you have what you have seen. If you have already recorded IR spectra ever in your college life, if you will understand that the IR spectral regions corresponds what you have read, this CH, C bond, CH bond, CC bond, NH bond, all these comes to the group vibration, and this skeletal vibration is actually known as fingerprint region. Fingerprint region. Okay, because the spectra you can see over here, this looks like a fingerprint. Okay, so the then designation of the skeletal vibration and group vibration from IR spectra and order of vibrational frequency in terms of mu A and mu. What should be the vibrational frequency? That was calculated. That is a comparison of C, single bond C, double bond C, triple bond C. You can compare these things because all CC bonds to all of them are CC bond. The only difference is their constraints. So in terms of K, how is your vibrational energy will differ. From that you can calculate what should be the vibrational frequency. Okay. In the next lecture of lecture number 36, which was taught by Professor Anirban Hajra, and he has introduced some concept that for a polyatomic molecule of n atoms, the potential energy should be a function of 3n minus 6 coordinates. Okay, so potential energy will be a function of all the 3n minus 6 coordinates. Okay, so for nonlinear case, I am writing it. So, and then also the potential energy can be written, that is a sum of 3n minus all 3n minus 6 different one-dimensional potential energy, and this is true only in normal mode coordinate. Now we are only discussing about, since we are only discussing about the normal mode coordinate, so this is possible in normal mode coordinate. So I can write this total V, which is a function of R1, R2, Rn. I can write it approximately as, or Xn, I can write it as V of R1 plus V of R2, R3n minus 6. This will be 3n minus 6 because I have said 3n minus 6 vibration will be there. Plus it will be V of R 3n minus 6. This should be R 3n minus 6. Okay. So I can write this total vibration of the system in terms of vibration of every single one-dimensional 3n minus 6 different potential energy. Similarly, I can write the total Hamiltonian. Also, I can write it in terms of simple individual one-dimensional harmonic oscillator. Like I can write if HQ of Q1, Q2, I can write it in terms of H of 1 into Q1 plus H. So I can separate this Hamiltonian with respect to each coordinate. Okay, plus H of n minus 6 and Q of n minus 6. Okay, so I can write this total Hamiltonian in terms of this one. Then it was shown that in normal mode vibration, all the atoms move such that their center of mass is not changed. Center of mass will not change. So if something is stretching over here, the above atom which is there, so it will come down to maintain the center of mass. Okay, so you can see for For a polyatomic molecule, the movement of one or more atoms there corresponds to a movement of all the other atoms in the molecule. And then it was shown that using the same concept that how is the vibration of carbonyl group is changing with different atoms are present. Okay, it was shown that when oxygen is present out there, or oxygen carbon is when nitrogen is present on conjugation to this carbonyl, how this vibration is happening. Okay, because of addition of different atoms which have different masses, so this vibration will be different for each cases. So this was the discussion for rotational vibration spectroscopy. On a short case, I can say that there was a discussion on the P and R branch, why P branch lines are spaced far apart from each other, where R branch lines are very close to each other. And then there was a discussion on Q branch line. Then there was a discussion on normal mode coordinates, how many number of normal mode coordinates could be there. And from that, from the symmetry and group theory, what should be the normal modes are responsible for carbon dioxide and water. That was discussed. And under which condition the selection rule will be the selection rule will be followed, and and you will get maximum intensity. That was also discussed. And then the two lectures here that you can see here, that there was a discussion on perpendicular and parallel mode of vibration, and you can see under which condition this Q band will be generated. And then there was a discussion on skeletal and group vibration. What is skeletal vibration? That is the vibration of one symmetric or bending, stretching or bending mode will affect another. But in group vibration, that vibration is separate, which is separate from the rest part of the molecule. Then there was a lecture which discussed about the you can write this total total potential energy as a sum of individual potential energy. Then it's like the Hamiltonian. You can also write this Hamiltonian as a sum of different Hamiltonians. And also it was finally discussed that if there is a vibration of a molecule, the center of mass is not going to change. So this was all the discussions. Now I'm going to solve some questions regarding this week. So this is my first question. In enharmonic oscillator, when we go to the higher vibrational level, then compared to ground vibrational level, so three options you can see that one thing is common, that is they have asked about the fate of rotational constant. Okay, they have asked about whether rotational constant is decreased, whether rotational constant will increase, whether rotational constant remains same. What is rotational constant? Rotational constant is nothing but B. So, in a simpler way, if I am going to simplify the question for you, if there is a transition from V equals to 0 to V equals to 1 level, okay, so what I have said you that if there is a transition from one vibrational level to another, B values will be changed. Okay, so for V0 is suppose it is V0 and suppose it will be V1 for V is equals to 1 state. Now, which one is higher in which one value is higher, V0 or V1? So this is the question. So can anyone guess which should be the answer? Yeah, can you guess which should be the answer? I've discussed it. You wanna try? Okay, so I'm discussing. You can find this answer also in lecture number 32. So this is the answer. That for any vibrational level, B can be defined, what I have written in the formula in the previous discussion, that how can I define B? So B as a function of vibrational quantum number V, it can be defined as BE minus alpha into V plus half. Okay? So this is the dependence of this V on this rotational constant at any vibrational level. Okay, so you can clearly see that if V increases, So there will be increase in V plus half value. Then alpha into V plus half, well, alpha is a non-zero constant, it will increase, right? So considering VE is equals to constant, so if V increases, then this total value, this alpha into V plus half, this total value will increase. Okay, so you can this will increase. This total part will increase. Okay, if V increases, this V plus half will increase. Also, since alpha is a non-zero value, so this alpha non-zero constant will increase since it is multiplied by V plus half. Since this plus is increased, and if B is constant, then you know that what should be the fate of BV. That is, your BV will decrease, right? So your BV, that is the vibrational, this rotational constant of the upper vibrational level, that will get decreased. So what should be the answer? So increase in V will actually decrease the BV. So the answer is the rotational constants decreases. Got this answer? Okay, so I'm moving to the next question. Which one? Okay, so it is my next question. That is, in an enharmonic oscillator, when we go to higher vibrational level, then compared to ground vibrational level, the same type of questions, but I have put it in the next question because there is something you need to calculate much more. That is, what should be the fate? Now it is asking about average bond length. Average bond length. Okay, that means you have to find what should be the fate of heart. If you are going from a ground vibrational level to a higher vibrational level, what should be the fate of heart? It will increase, decrease, or remain the same. What should be the answer? Okay, so I'm going to discuss that. You can also find this in lecture number 32. And also in find in lecture number 32. And this is the explanation. That is, for any vibrational level, B can be defined as BV is equals to BE into minus alpha into V plus half. So if you increase, there is an increase in V, it will decrease your BV. Okay, what I have discussed in the last question, that is, what should be the fate of B as you are increasing this V. So BV is equals to BE minus alpha V alpha into V plus half. Okay, so this will be the fate of B, okay, with change in V. So what is said, when you are going to higher vibrational level compared to ground state level, what will change? So higher vibrational level means your V increases, right? And then from that we have shown if B increases, then B should decrease. So your B should decrease. Okay. So if you have increased V, that is your V is increasing, then your B should decrease. Okay. Now, what is the formula of B? B can be written as H by 8 pi square IC. Okay. So you can see B is indirectly proportional to I. Okay. So B is indirectly proportional to I. So if B decreases, then what should be the fate of I? So if B decreases, since it is inversely proportional, so if this decreases, then it must increase. So I increases. Okay. So you have understand what should be the fate of this B on changing this vibrational energy level. Okay. So if vibrational energy level increases, your B should decrease. If B decreases, since B is inversely proportional to I, that is moment of inertia, so if B decreases, I should increase. Now, what should be the value of I? I is equals to mu r square, right? So, I can write I proportional to r square, right? So, if I is directly proportional to r, so since it is directly proportional, so if I increases, then r also increases. Okay. So you understand this terminology changes. That is, your V is first of all when you are going from ground vibrational level to excited state vibrational level. First of all, what should increase? Your quantum number will increase. Okay, your vibrational quantum number will change. You will get a higher vibrational quantum number. So with this higher vibrational quantum number, what else will change? Will be there is a change will be in the V value. Okay, so B will get decreased. So if B is decreased, then since you have seen B is inversely proportional to I, so I will increase. And also you have seen this I is nothing but mu r square. Okay. So I is nothing but mu r square. And also from this we can show that I is proportional to r square. That means if I increases, R will increases in by square. Okay. So if I increases, so R increases. So finally, it is seen that from this all these four lines here written, so I'm changing this color. So all these discussions is getting us to one single final conclusion that if V increases, then R increases, right? So this was also already this was asked in your questions that if what should be the fate of R if V is increased? You find your answer that if your V increases, your R will increase. Okay, so you can sir, you can so what is R? R is your average bond length. Okay, so if your V increases, then R will increase and average bond length will increase. So the final answer is average bond length will increase. This one. Okay. Okay, now I'm moving to the next question. It is a very straightforward question. Identify the correct statement. Delta J is equals to 0 is Q branch. Delta J is equals to 0 is P branch. Delta J is equals to -1 is P branch. Delta J is equals to -1 is R branch. Okay. So what should be the answer? Which are the correct statements? Okay, so I'm going to discuss this question. if you want to find this answer, you can find in the lecture number 32 that what should be the fate, sorry, what should be the proper selection rule and which branch corresponds to which transition. Okay. So you know, therefore delta j is equals to -1, it corresponds to P branch. Okay. If delta j is equals to 0, this corresponds to Q branch. And if delta j is equals to 1, this will correspond to R branch. So if okay, suppose this is my V is equals to 0 level, and this is my V equals to 1 level. Now, if there is a transition, now if there is a transition from this level to so if there is a transition in this way, there is a transition from this to this level, this is a straight arrow. Okay. So if this is the transition, I'm writing another transition in the another color. Another transition I'm writing. Okay, so I am writing three different transitions: in green, in blue, and in yellow. Okay, so this transition corresponds to delta j equals to -1. This is nothing but P branch transition. This corresponds to transition delta j is equals to 0. So this is called Q branch transition. And finally, this yellow transition, which is Q corresponds to delta j is equals to +1. So this is R branch transition. Okay, so there is a simple way to remember it whenever you have forgot which branch is what for generally for P, P and N branch. So I will tell you that just write delta J, and you know these three values are possible: -1, 0, +1. Write it in the increasing order, just and then put P, Q and R. So your delta J is equals to -1 corresponds to P branch, 0 Q branch, +1 R branch. This is simple as that. Okay. So you have got your answer now. So what should the answer? The answer will be that delta j is equals to 0 is a Q branch. This is correct. But delta j is equal to 0 is not a P branch. Delta j is equals to -1 is a P branch. This is correct. But delta j is equals to -1, it is not an R branch. For R branch, delta j should be equals to plus. So this is the answer. Okay. Okay. So I'm moving to the next question. So vibrational mode for n atomic polyatomic molecule, what should be the vibrational normal mode? Okay. So vibrational normal modes are, I have discussed also this question in reference of lecture number 33, that for normal modes of vibration for n atomic molecule can be defined for n atomic molecule if this molecule is linear what should be if this molecule is non-linear. So I'm going to calculate that. Okay. I have given you this statement. The 3n minus 5 will be for linear and 3n minus 6 for non-linear cases. For non-linear molecule, this will be 3n minus 6. Okay. So I'm going to discuss why this is 3n minus 5 and why this is 3n minus 6. Before that, for one atom, what should be the mode of vibration? 3 different. 3 degrees of freedom. Okay. That means, suppose when I have one atom, I can move it to the x direction, I can move it to the y direction, I can move it to the z direction. Fine. Now, for if n atoms are there, then there will be 3 into n, that is 3n number of degrees of freedom. Okay. So that means if I have one atom, I have 3 degrees of freedom, but I have n atoms, I have 3n number of degrees of freedom. Now, basic question, out of this 3n number of degrees of freedom, why I'm writing, I am making just a table that type of molecule. Okay, let me make this this way. There is, I'm making a table for type of, under this category there should be so in my left side I am writing linear molecule, on my right side I am writing non-linear molecule. This side I'm writing degrees of freedom. Okay, so I'm writing degrees of freedom on the left side, and how much there is degrees of freedom for these two different molecules I'm going to discuss that. So starting from this beginning, okay, so first of all, translational. So a molecule that is linear, it can move to either x, either y, or z. Okay, so it can move in any of these three directions. So it has three translational degrees of freedom. Same for the nonlinear case. This nonlinear molecule also can move to three different transition levels or three different axes, along three different axes. So similarly, just like the translational degrees of freedom for nonlinear molecule, there should be three translational degrees of freedom. Then there is rotational degrees of freedom. Okay. So for linear molecule, how many rotations are possible? Since linear molecules means it is situated in a particular plane. Okay. And since it is in a plane, it doesn't have that much of degrees of freedom, just like a nonlinear molecule. So it will have only two different types of rotational motion. But for nonlinear case, there will be three different rotational motion. Okay. So nonlinear molecules, since they are not in plane, for nonlinear molecules, since all the atoms are not in the same plane, so there will be another rotational degrees of freedom. So how much is the total? So you have to calculate what should be the vibration. So you know total number of degrees of freedom is 3n. Okay. Total number of degrees of freedom is 3n for each case. Now, translational motion has 3 different degrees of freedom. Rotational motion has 2 degrees of freedom. So total 5. So remaining from that is 3n minus 5, there will be vibrational degrees of freedom for linear molecule. Or similarly, for non-linear molecule, since translational motion and rotational motion both have 3 different degrees of freedom, the total number of vibrational degrees of freedom will be equals to 3n minus 6. Okay. So for non-linear molecule, number of vibrational degrees of freedom or normal modes, 3n minus 6. For linear molecule, this will be 3n minus 5. So this is your answer that you have want to find here. That is 3n minus 5 for linear, 3n minus 6 for non-linear.
Sir, I have one doubt, sir. Linear, transition is 3 and rotational is 2. How do you, sir?
Sorry.
The difference between 3 and 3, 2 and 2, how do you put?
Okay, okay. So translational means this molecule can move in either of these directions, X, Y, or Z. Okay, you can move this molecule in either X direction or Y direction or Z direction. So this is possible for whether it is linear or non-linear, you can move it to any direction. But when there is a linear molecule, the rotation, the linear molecules means all the atoms are situated in a particular plane. Okay, so if there will be some restriction about the rotation with what say without the plane, that means out of the plane rotation. Yes, out of the plane rotation, this is not possible for each atom. So there will be 1 degree of freedom or 1 rotation that will be restricted for linear molecule. But in case of non-linear molecule, since all the atoms are all not in the single plane, so the movement, all the rotational degrees of freedom will be there. So only 3 degrees of freedom will be there for rotational molecule in non-linear system. But for linear system, since it is in a particular plane, so only 2 motion are there. 1 motion is restricted. That is out of plane movement. Okay, you have understand?
Yes, sir. Thank you, sir.
Okay. Okay. So your correct answer is 3n minus 5 for linear, but 3n minus 6 for non-linear. So I am moving to the next question. That consider a transition between ground state with symmetry B2 and excited state with symmetry A1 in water molecule. If the transition has to be allowed, what should be the symmetry of this dipole moment operator? So this is the question. You want to try? So it is said that you have to consider a transition between a ground state which have symmetry B2. Suppose I am writing a ground state and then excited state. Okay. So your ground state will have symmetry B2 and excited state will have symmetry A1. Okay. So if the transition has to be allowed, what should be the symmetry of this dipole moment operator? So I'm making this question much easier for you. Yeah. Okay. So so allowed transition, that is the intensity of transition intensity of transition, you know, I can get from transition moment integral. Right? So I can get if what should be the intensity of transition of my system or for this kind of transition, I can get this value from the calculation of transition moment integral. Okay. So this value will be psi f star mu psi I. I have discussed it several times. It will be detailed. Yeah. So this is my transition moment integral. Now I have said that you have this psi f star, which is your final state, or in this case, which is the excited state. This has symmetry A1. You have mu here, and the final state will have a symmetry that is mentioned as P2. So you need to tell what should be the symmetry of this one such that this integral is non-zero. So this is the question, that what should be the value of mu, that is how mu will be there, that is what should be the symmetry of mu, so that this total integral is non-zero. So what should be the answer? Okay, fine. So you can find this answer in lecture number 34. That transition moment integral is defined as mu f star mu psi I. So transition moment integral can be defined as mu f psi f star mu psi I. So if wave function have B2 or A1 and A1 symmetry, then to have an intense transition, the dipole moment operator has to have how? Because I have said earlier that to have an intense transition, you need to have your total transition moment integral of A1 symmetry, because A1 symmetry is a totally symmetric configuration. Okay, under this condition, this transition moment integral will be z non-zero for any molecule. Okay, so if multiplication of all the symmetry elements if will give you this A1, then your symmetry transition moment integral is not zero, and your the transition is very much intense. So to make this A1, we are doing back calculation. That means you have there is A1, so mu must have something which will multiply with B2 to give some A1, right? Because I have to find A1 is equals to A1 into cross A1 cross mu. That means there will be something. Yeah. So there should be something. Then it will be multiplied by something of B2 symmetry, so that total symmetry is A1 symmetry. So suppose, so you can see here there is A1 already there. So I now have to find something which will multiply with B2, give me the same configuration. So there should be something that will multiply with it to give this A1. So I need something that will multiply with B2 to give A1. And there is nothing, if you have seen this character table, only B2 is possible, which will multiply with B2 to give A1. Okay. So your dipole moment must have symmetry B2 to have this intense transition. Okay, because if it is not B2, it will multiply with B2, and then there should be not give you should not get A1, then your transition will be not allowed. But if it is B2, then it will multiply with B2 to give A1. A1 into A1 will give you A1. Okay, so that final answer is okay. Okay, so I'm moving to the next question. Here it is asked that skeletal vibration is normally referred in which region? So I have discussed this completely, that in which region this skeletal vibration happens. So I'm just repeating this, that your vibration can be defined as in two category. One is skeletal vibration, another is group group vibration. That means skeletal means what I have said, that your one vibration, your vibration, your stretching and bending modes will be coupled up to give some vibration. So from that you cannot distinguish which kind of functional group is there. But from group vibration, you can easily calculate that this functional group will come here, and so you can distinguish them, because in group vibration, one vibration is independent of the rest part of the molecule. So skeletal vibration is also known as fingerprint region in the IR spectrum. Because in this region, the spectra look like a fingerprint. This is also known as fingerprint region. Okay, so we'll find this answer in lecture number 35, that skeletal vibration arises what I've shared from coupling of stretching and bending vibrations of atoms in long straight chain in a ring. They generally appears in the range. This is the range 7,100 to 14,000. So it should be 15,000. That's quite fine. No problem. So it appears in the range 700 to 1400 centimeter inverse in the IR spectrum. Okay, so this is a straightforward question. You are known this answer. So the answer will be is 700 to 14,000 centimeter inverse. Okay. So this is also a straightforward question. You know the answer. So what should be the symmetry point group of water? So you can also find. You want to try? You want to try? Which should be the answer? Okay. So this is the character table. This is called character table of water molecule, and this is the group symbol you have written. You have seen that this is the point group of water, and you have seen it is the z-axis, this is the y-axis, and this in this direction there is x-axis. Okay, so there are four different vibrational modes. There are four different kinds of symmetry, and from this there was just calculated that two A1 symmetries are there and one B2 symmetry is there for water molecule. And then the point group, you can identify that if you find what are the symmetry elements that is present in water. So identity is always there, E is always there. You know, for water molecule, if in this direction, if z direction, if I use a C2 axis, that is, I rotate it by 180 degree, these two hydrogens will be interchanged, and but the configuration is same. So it will always have C2 symmetry. Okay, and also in this direction, upon xyz, xz plane and yz plane, you can see there are two symmetries will be there. Okay, so there it will have two sigma v planes corresponds to xz and another corresponds to yz. Okay, two sigma v planes will be there. So since it has such configuration E C2 and 2 sigma V, so it corresponds to a point group which is denoted as C2V. Okay. Now, if any higher kind of, if any higher in the, just note it that if any higher kind of rotation is possible, that is C3, C4, C5. Suppose I have in this point, this is a point group. I want to tell something that if along with identity there is Cn axis and in situ axis are there. Okay, if you have find that in your normal linear structure that You have, suppose you have C4 axis and 4 C2 axis, or C5 axis, 5 C2 axis. Okay. If you find that, then this will go under the category of D point group. Okay. This will go under the D category point group. And if in your system you have both sigma H and sigma V, your sigma H will be preferred. So this will have configuration of DH. Similarly, in C system, if instead of sigma V, if there is a sigma H kind of thing, which is not present here, but suppose if it is there, then your total this point group will become C2H. Okay. Now I'm coming for water. You can see from the symmetry elements, it becomes the C2B point group. Okay. Okay, fine. I'm moving to the next questions. So benzene has how many normal mode of vibrations? Okay. Okay. So benzene has how many modes of vibrations? Is it 20? It is 30? Is it 29 or 31? So how many modes of vibration will benzene have? What should be the answer? So I have already said for any n atomic molecule, if it is linear, then what should be the number of normal modes? This will be equals to 3n minus 5. And if it is non-linear, then what should be the number of normal modes? Number of normal modes will be equals to 3n minus 6. Okay. So for any n atomic molecule, if it is a linear molecule, the number of modes will be 3n minus 5. If it is non-linear molecule, then the number of normal modes will be 3n minus 6. Now you just need to find what is the atomicity of benzene and atomicity of benzene. Two questions you need to find. And second question, this is the first question, and second question, what kind of molecule is benzene? Is it linear or non-linear? So two questions you need to find the answers. If you find these two answers, you will get the answer. So you can find this answer also in lecture number 34. Whenever there was a discussion on normal modes, that it was said for normal modes, for n atomic molecule, it is 3n minus 5 for linear and 3n minus 6 for non-linear, what I have discussed so far. And now, atomicity of benzene, it is, how can I get 12? So everybody knows the structure of this benzene, which is C6H6. That means you have in benzene there is 6 carbon atoms and 6 hydrogen atoms. Total 12 atoms are there. 6 carbon atoms and 6 hydrogen atoms. Okay. And now you know benzene is a non-linear molecule. Okay. So then since benzene is a non-linear molecule, so which will apply here? Here will be applied 3n minus 6 rule. Why it is non-linear? Because all of these atoms, suppose if this C double bond C's are there, if it is in the plane, but the hydrogens are not in plane. Okay. So this is completely non-linear molecule. Okay, so for benzene, n is equals to 12, and you have to follow this 3n minus 6 rule. So n 3 into 12 minus 6. 36 minus 6, it is nothing but 30. Okay, so here it is your correct answer. That is, for benzene, how many normal modes of vibration will be there? There will be 30 normal modes of vibration. So correct answer is 30. Okay. Okay, fine. So I'm going to the ninth question for today. That is, for rotational vibrational spectra or polyatomic molecule, which of the following is or are true? That is, for parallel mode, delta J is equals to plus minus 1. For perpendicular mode, delta J is equals to 0 or plus minus 1. For parallel mode, delta J is equals to 0 plus minus 1, and which. That means here in your question, you have asked to find first question. Just understand the question. Here you need to find a selection rule for parallel and perpendicular mode. This is my first question, and you have seen in the option there is something about Q branch. Why Q branch cannot be seen in parallel mode? I have said that whenever there is a perpendicular mode, you will only see this Q band. But for parallel mode, you cannot see this Q band. Okay, so what should be the answer? So for this question, you can find this answer in also in lecture number 35, that for parallel mode, the selection rule regarding rotational transition is only the selection rule is delta J is plus minus 1. This is the selection rule regarding parallel mode. That is, for parallel mode, the selection rule is delta J will be equals to plus minus 1. Fine. But for perpendicular mode, I have said that for this perpendicular mode, delta J should be equals to 0 or plus minus 1. These two values are possible. Okay. So for parallel mode, your delta J should be plus minus 1. And for perpendicular mode, delta J is equals to 0 is also possible. Why it is possible? Why it is showing for bent molecules, or why it is showing for not bent molecule, like for kind of thing, and why it is showing mainly for it is related to the bending vibration. I've discussed that. Okay, because for perpendicular mode, it is seen that this angular momentum doesn't, which was initially corresponds to this rotational transition, it is now included in the vibrational transition. So delta J is equals to 0, it is coming there. So first question, that selection rules for parallel and perpendicular mode, we have find that. Now we have to find which options corresponds to these two answers. The first question option is, for parallel mode, delta J is equals to plus minus 1. And for perpendicular mode, delta J is equals to 0, plus minus 1. Yes, this is the correct answer. This is correct. That for perpendicular parallel mode, delta J is equals to plus minus 1. What we have discussed, And for perpendicular mode, delta J is equals to 0 and plus minus 1. For parallel mode, this is not correct. Now, the second question is, when will be Q branch seen? So, you know the condition under which Q branch will be seen. The condition is delta J should be equal to 0. Now, you have to find in which mode delta J is equal to 0 is there. So, you can see in perpendicular mode, delta J is equal to 0 is there. So delta J is equal to 0 is present in this perpendicular mode. So you only see this Q branch can be seen only in perpendicular mode. Okay. So my 3 and 4 options I have to find that Q branch cannot be seen in parallel vibration because of delta J is equals to plus minus 1 only. Is this true? Why this is not happened in parallel vibration? Because in parallel vibration, delta J is equals to 0. This is not possible. Okay. So my answer will be this first one and the third one, because Q branch cannot be seen in parallel because delta J is equals to plus minus 1 only. There is no delta J is equals to 0. Okay. Okay. So I'm moving to the next question, that match the correct combination. CO2 has 5 rotational degrees of freedom and 3 vibrational degrees of freedom. N2 has 2 rotational degrees of freedom, 1 vibrational degrees of freedom. CO2 has 3 rotational degrees of freedom, 4 vibrational degrees of freedom. And Na has 1 rotational degrees of freedom, 1 vibrational degrees of freedom. Now I'm going to calculate each for them. Okay, so I would like to make a table of all this. So you can find also this answer in lecture number 34. So I'm writing here degrees of freedom just like the previous table. I'm writing here these molecules by one. Yeah. Okay. So I have written 4 there. So you have to find that which combination is correct. Okay. So from these degrees of freedom, so you know that for first you need to find what is the total degrees of freedom. So see carbon dioxide, which is how many atoms, how will be the atomicity? The atomicity will be 3. That means 3 atoms are there. So how many number of degrees of freedom? Total 3n. Total 3n. Okay. So 3n among, so there is 3, so 3 into 3, that will be 9. 9 degrees of freedom will be there for carbon dioxide. For nitrogen, since it's a diatomic molecule, so n equals to 2, and 2 into 3, that will be 6. Okay, so I'm writing, if everybody is confused with it, I'm writing it. So total number of degrees of freedom I have mentioned earlier, it is nothing but 3n, where n is the number of atoms present in this molecule. For CO2, you can see 2 oxygens, 1 carbon. So 3 atoms are there. So following this rule, there will be 9 degrees of freedom. For sodium, since it is only 1 atom, so there will be 3 degrees of freedom. Okay. So we have calculated what should be the total number of degrees of freedom on each molecule. Now I am going separately. Okay. So this is translation. This is rotation. There should be vibration. Okay. So I'm going one by one, and you will then match answers. Okay. So for carbon dioxide, I'm going one by one. So for carbon dioxide, I have said that 3 translational degrees of freedom will be there. So you have already calculated for carbon dioxide. Carbon dioxide is a triatomic linear molecule. Okay. Carbon dioxide is linear. So its rotation in the out of plane is already prohibited. So it will have only 2 rotational degrees of freedom. So how many number of vibration will be there? So vibration will be like how many? 3 and 2, 5. Total 9, and among these 3 are translation, 4 rotation. So 9 minus 5 equals to 4. So for carbon dioxide, 4 vibrational degrees of freedom will be there. Okay. So you understand for carbon dioxide, that is a linear molecule, triatomic molecule, 3 translational degrees of freedom will be there, 2 rotations will be there, and 4 vibrations will be there. Okay, so I have written CO2 twice. Okay, fine. So I have calculated it, so I don't need it. Okay, so rather than doing that, I will cancel this. Write sodium here. So total number of division 3. Yes. So for nitrogen, which is a diatomic molecule. So how many number of translations? There will be 3, because for every case you can see every molecule can move in these 3 directions. Okay, X, Y, and Z. So 3 translational degrees of freedom will be there. Now, what should be the rotational degrees of freedom for nitrogen? Nitrogen will have just like CO2, because since nitrogen is a diatomic molecule, so its rotation will be just like CO2 in the plane. Okay, CO2 is a linear triatomic molecule. All the atoms reside on a single plane, and nitrogen is a diatomic molecule, so it will be also in plane. Homogeneous diatomic molecule, so it will be also these 2 atoms, nitrogen atom, will be in the same plane. That's why its rotation will be similar like that of carbon dioxide. Okay. And now, how many number of degrees of freedom for vibration? So 6 minus 3 plus 2 will be 5. So we'll get 1. Okay. Now, for sodium, I have said that 3 translational degrees of freedom will always be there. Since it has total 3 degrees of freedom and it is a single atom, sodium atom, so you can understand, since it is a single atom, it neither it can rotate nor it can vibrate. Okay, so it can just move from one direction to another. So it will only have translational degrees of freedom. Okay, now I have to match all these of these varies. First option is CO2 has 5 rotational degrees of freedom and 3 vibrational degrees of freedom. No, CO2 has 2 rotational degrees of freedom and 4 vibrational degrees of freedom. So this is not correct. Nitrogen has 2 rotational degrees of freedom, 1 vibrational degrees of freedom. Yes, this is correct. You can see here. This is 2 rotational degrees of freedom, 1 vibrational degrees of freedom. Okay. So you have got your answer. Now you have to find, so you have to see that if other answers are correct or not, always see that. Okay. So if CO2 has 3 rotational degrees of freedom and 4 vibrational degrees of freedom, no. Your number of vibrational degrees of freedom is correct, but there is no 3 degrees rotational degrees of freedom. There will be only 2 rotational degrees of freedom. And sodium has 1 rotational degrees of freedom and 1 vibrational degrees of freedom. No. Sodium is a single unit molecule, atom. So it neither vibrate nor rotate. So only 3 rotational states will be possible. 3 translational translational motion will be possible. Rotational degrees of freedom and vibrational degrees of freedom will be 0 for sodium. So correct answer is nitrogen 1. And nitrogen has 2 rotational degrees of freedom and 1 vibrational degree of freedom. Nitrogen has 2 rotational degrees of freedom because it almost behave like that of carbon dioxide. Okay. Okay. So one more question I am going to ask. Which of the following vibrational stretching mode has lowest vibrational frequency? Here there is SH, CH, NH, OH. Different vibrational modes are there. You have to find which one of these will give lowest vibrational frequency. Okay. So here you know what is the formula. The energy of the stretching vibration can be expressed in terms of nu, which is which we can write as 1 upon 2 pi root over of k upon mu, right? So this is the vibrational stretching frequency or vibrational stretching wave number, vibrational stretching uh, wavelength, whichever you can convert, but the general expression is nu is equals to 1 by 2 pi root over of k by mu. So what factors this mu depends? Mu depends upon this k, which is nothing but the force constant, and this is the mu will be there, which is reduced mass. So your mu, your nu, that is the vibrational stretching frequency, it will depend upon two factors. One is force constant, another is reduced mass. Okay. Suppose for mu, now mu for which of these following will be? So my question is lowest vibrational frequency. That means mu will be lowest. Mu lowest. I am going by back to back calculation that I need to find for which value of k mu will be lowest, or which value of mu will be lowest. Okay. So nu lowest means your k will be lowest. Also, your mu need to be highest because mu is in the denominator. Okay. So for nu need to be for nu to be the lowest one, your k need to be the lowest one. Also, your mu need to be the highest one. Okay. So k need to be the lowest one. That means, okay, I am coming of k after this. First, I am going talking about mu. So for which case mu will be highest? You know that mu for, if you calculate for HH bond and HD bond, you can see that for HD bond, mu will be higher. Okay, because you can easily see what is the expression of mu. Just logically, you can think it as mu m1 into m2 divided by m1 plus m2. So you know, if two numbers are there, if you are adding them and if you are multiplying them, if the multiplication will give bigger result. Okay, so mu value will depend upon m1 into m2. Whether if m1 or m2 is higher, this mu will be higher. Okay, so among these you have to find which one is have highest mass. Okay, hydrogen is constant for everything. So among oxygen, nitrogen, carbon and sulfur, you know the sulfur is lower in the periodic table, so the sulfur will have highest mass. So for SH bond, SH bond, SH bond, mu will be higher, right? For SH bond, you see, for SH bond, this mu, that is the reduced mass will be higher because sulfur is higher in mass than the other salts. Okay, but this is all not all the thing. Okay, now to find what should be the value of k, and you know if you are going through this periodic table, you know S is the third period element, all the others are second period element. Okay, so if your period element is getting by one, then your bond length will increase. Fine. So if your bond length is increased, so k will be very low, right? So if bond length is increasing, that means your two atoms are going far away from each other. If the bond length is decreasing, that means if it's coming to single, to double, to triple, these atoms will be coming closer. But if you are going through second period to third period, these atoms are getting bigger in size, so the bond will be getting longer. Okay, so that means K will be low. So you see for this SH bond showing the two conditions, highest mu, also lowest K. So since SH bond shows these two conditions, highest mu and lowest K, so it will have lowest mu bar, mu lowest for SH, or mu lowest for SH. So your answer should be SH bond. Understand that? Okay. Okay, fine. Okay, so I think I have discussed some questions regarding this week's assignment. So all I have to discuss, I have discussed. Now you can solve your questions, and if you have any doubt, you can. I will upload this video in the YouTube, and you can ask their question. Okay, you can, or you can ask me questions for the next class wherever you want. Okay, so I have to close this live session if you don't have any questions. Do you have any questions up to this? Ashwini, do you have any questions? Okay, fine. Okay. So I'm stopping the recording first.